It's working? Yes, it's working. So good morning. Okay, so last week we saw thermal equilibrium. Okay, we had different types of problems, but one of the types was equilibrium problems. Okay, another type which is not equilibrium is when you have to heat up something and you need to know how much energy it takes. But in equilibrium, you remember that we had the equilibrium equation, the Q received plus the Q given is equal to 0. And I explained you that the Q received is positive, the Q given is negative. And so we could have this equilibrium equation Q received plus Q given is equal to 0. Okay, so now we are going to do a certain number of these problems. We are going to correct them, and later we are going to introduce, I don't know if we will have time today, what happens when we have phase changes, okay, which includes an additional difficulty. Okay, so one exercise I gave you to do was 5. Okay. Did you do it? Were you able? Yeah? Okay, so let's correct it. We have water and we have an iron vessel of mass 300 grams. There is somebody who's eating his mic. No? Or hitting it. Okay, now it stopped. Okay, so this is an equilibrium problem. Okay, clearly, because this is asking you the equilibrium temperature. So we treat it like an equilibrium problem. We write the equilibrium equation, and then we write the different terms. Okay, we have 200 grams of water. Okay, so let's start writing this term. I will write it first literally. It's the mass of the water times the C of the water times the final temperature, which is of course the equilibrium temperature, minus the initial temperature of the water. That's the term for the water. Plus there is a term for the iron. Okay, the chemical symbol for iron is Fe, comes from the French, times the C of iron, times the final temperature, which is the same for the iron as for the water, minus the initial temperature of the iron, and this should be 0. Okay, actually, you just write one term like this, mc delta T, for each component of your system. And if you write it properly, it will have the correct sign. You see this one will be negative because the water becomes colder, and this one will be positive. This one will be negative, this one will be positive. But it's automatic due to the choice here of the initial and final temperatures. Okay? Okay, and what we are looking for is the TEC. Okay, so let's now write in the numbers. The mass of the water is 0.2 kilograms. You always put it in kilograms. The C of the water is 4,180. And then we have TEC minus the initial temperature of water, which is 50 degrees. Okay? Then we have the iron vessel. The mass is 300 grams, so 0.03. The C of the iron, how much is it? 450? You have it? Or should I? Sorry? 450. Okay. Times TEC minus the initial temperature of the vessel, which was 20 degrees, and this is equal to 0. Okay, now if you are a bit used with that, you can do it in one step. The equilibrium temperature, it's going to be The numerical terms above the fraction bar, so it's going to be 0.2 times 4180 times 50, okay, and the minus sign disappears because you have put it on the other side of the equation, plus 0.3 times 450 times 20. This is the second term here, and this is divided by the coefficient of Tx, which is 0.2 times 4180 plus 0.3 times 450. Okay? Now, what did you find for that, those of you who did it? You have 45.8. Water at 50, iron at 20. Yes, the iron. So, do you think this is possibly correct? How do you now check whether this corresponds to what you are expecting actually? Do you think this is correct? Yeah. Why? Exactly. So the water has more influence, and so the temperature of the water just decreases by 4.2 degrees, while the temperature of the iron increases by 25.8, which is to be expected because water takes more energy to warm up or cool down than iron, okay, approximately 10 times more, okay? So this is, I'm not going to check it, I trust you, plus the result looks nice, so that's fine, okay? Did anybody have difficulties with this? No? Good. Okay, so let's continue. And now we have another one. Does somebody want to correct it online? You can tell me what you want me to write and I can write it. No? Well, now it's the same exercise but with oil instead of water. Okay, it's the same iron vessel at 300 grams at 20 degrees. It's the same initial temperature of the oil. It's the same quantity of oil as of water in the previous exercise. So it's all going to be similar except for the final result. So we can now take the result from the previous exercise, copy it, and just change one value, okay? Here we can redo Tx is equal. We had 0.2 times the C of the water, but now the water has been replaced by oil, okay? And the oil is 1870, so I changed that, times the initial temperature, which was 50 plus 0.3 times, this is for the vessel, which hasn't changed, 450 times 20, divided by 0.2 times 1870 plus 0.3 times 450. Okay, I don't redo the whole calculation because it's exactly the same. The only thing that changes is this value here, where previously we had 4180 for the water, and now we have 1870 because it's oil. Okay? And how much did you get as a numerical result? 40. 42.04 degrees. Sounds very good. I will trust you for the calculation. So if it's wrong, you need to scream at, I don't know who it is. I didn't recognize the voice, but you guys know. Okay, 42.04. You see that in the previous exercise, the temperature of the water was going down by 4.2 degrees. Okay, here the temperature of the oil is going down by 7.96 degrees, so about the double. Do you think it's correct? How do you understand that? Hmm? Well, you can understand it by the fact that the oil has a C which is about half, less than half the C of the water, and so the oil cools down more easily, and so it cools down more. It takes less energy to cool down, cools down more by about twice as many degrees as before. So sounds correct. Okay. Okay. Now in these exercises we were supposed to compute the equilibrium temperature. Now here we have another exercise where the unknown is not the final temperature. Okay, this we know because the question is how much water at 10 degrees should be added to the pan if we want the water to be at 50 degrees. Okay, so this question, how much water, this tells you that the unknown now is the mass of the water. So you need to rewrite the whole equation and then isolate the mass of the water, and you will be able to compute this mass of the water according to the other conditions. Shall I give you some time to do it? Okay, so the stage is yours, and I will go do a coffee. Okay, I'll be back in 2 minutes. This is I love confinement because I can do go coffees during the classes. It's great. I'll be back. Just tell me when you're done, okay? Done. Mm. More people have arrived. Wow. Yeah, there's new people. Alexandre has arrived. Alexandre. Alia. Alia. Alia is here. Dana, Emma, Aniel, Isalis, Laure, Maeva. Maeva, was she here before? Maeva. Yeah. Dana is not, she's never, yeah, she's here, Dana. Good. Dana, great. Dana. Eliana. What about Santiago? He cannot connect. What's going on with him? Does somebody know? Hello? Yeah, but come on. If I call his father, this guy is going to get beaten up. Maybe I should call his father. Because he wants his son to be strong. He watches it. Oh, okay. Yeah, okay. Okay. Good. Okay, can we correct it? Are you done? Okay. So, we have an aluminum. So, first I like it if you want to make me happy. Well, we're not going to have tests anyhow, but if you want to make me happy, write the equilibrium equation because this expresses what we are going to do, which is the conservation of energy, okay? And then we have an aluminum pan of mass 1.5 kilos. So let me write that before I write numbers. We have the mass of the aluminium times the C of the aluminium times the equilibrium temperature, which is now 50. We want everything to be at 50 degrees. And the initial temperature of the water is 60. Okay, so the water is going to lose energy. Okay, this is going to be negative. The aluminium. No, sorry. I made a mistake. An aluminium pan. Oh, yeah, it's correct. So because the aluminium pan initially contains 2 liters of water at 60, and so the aluminium pan, we suppose that it's in thermal equilibrium with the water. So the pan is naturally at the same temperature of the water, okay? So the initial temperature of the pan is also 60. And then you want to add water to that, but you don't know how much. So this guy is going to be the unknown, okay, times the C of the water, times the equilibrium temperature, which should be 50, minus the initial temperature of this water, which is 10 degrees, is equal to 0. Okay? We agree on that? So now let's write in the numbers. So the mass of the aluminium is 1.5 kilos. The C of the aluminium, you have it. It's 800, something like that. sorry, 900, 900 times 50 minus 60, so this is times minus 10. Okay, put the minus here in front. And then we have plus the mass of the water, which we don't know, the C of the water, 4,180, times 50 minus 10, which is 40, is equal to 0. And now, if you want to isolate this guy, you have to put that on the other side and then divide by the coefficient. So finally, the mass of the water will be equal to 1.5 times 900 times 10 divided by 4,180 times 40. Okay, is this what you found? So now how much does this give us? 1.5 times 9,000 divided by 4,180 divided by 40. No, that cannot be. Oh, yeah. It's 0.08 approximately kilograms, which is 80 grams. Is this what you found? Okay, yeah. What did I do? Maybe I'm not awake yet. This is the mass of the aluminium. Oh yeah, you are right. You are right. Yeah, sorry. Put that on the fact that I'm not awake yet, okay? Initially, we have the pan and we have the 2 liters of water. So sorry. God, my God, I'm very ashamed now. So we have to add, I will put it in red, we have to add a term for the water. This we will call mass of the water 2. Okay, and then here is going to be mass of the water 1, let's say, times C of the water. And what's the temperature difference of this water? Well, it's initially at 60 degrees and it goes down to 50 degrees, so we have to add this term, okay, somewhere here, okay? And this mass of the water, thank you, who said that? Aniel, yeah, good. Okay. Okay, you are compensating for a sleeping teacher. So indeed, we need to include that. And now this term comes where? It comes here in the sum. And we can put now the number. The mass of the water is 2 kilos. Okay, times the C of the water, 4,180, times 50 minus 60, so it's minus 10. Okay, and so we have to add this to the numerator. Okay, we pass it on the other side. So here we have plus, because we put it on the other side, 2 times 4,180 times 10. So this comes here. So because, yeah, 80 grams sounded like a bit strange, but I didn't remember the result. Okay, so now let's redo that. It's 1.5 times 900 times 10, so times 9,000, plus, and now we have 2 times 4,180 times 40, okay, divided by 4,180 divided by 40. This gives me now 2.08. Is this what you got? Aniela? 0.6. Why 0.6? Because this sounds much more realistic than 80 grams. I mean, if you have water at 60, you want to go down to 50. No, maybe this is a lot. Listen, let's redo it. Okay, let's redo it. I am very sorry. Okay, and let's do a small drawing because it can help when you are sleeping in the morning. Okay, so we have a pan of mass 1.5 kilos. We have 2 kilos of water. Okay, and the water is at 60 degrees. The pan is also at 60 degrees. And then the question is, how much water do you need to add? So this is the mass of the water that you need to add. And this water is at 10 degrees. Okay, so now let's write all our terms. For the water which is here, is going to be 2 times 4,180 times 50 minus 60. This is pretty clear. Okay, this is the water which is in here, 2 kilos, and is going from 60 initial temperature to 50 final temperature. Okay, then we have the pan. The pan is 1.5 kilos. The C of the aluminium is 900, and it's also going to go from 60 degrees to 50 degrees. And then we have this mass of the water that we need to add times the C of the water. And this water is at an initial temperature of 10 degrees, and the final temperature should be 50. Do we agree with this equation now? Oh, you don't even see it well. Do we agree with that? Is this okay now? Okay. So now we have that. Let's do it another way. Let's compute everything. So this is 2 times 4,180 times 10. And then there is a minus sign, so it's minus 83,600 for this term, okay? And then there will be a minus again, 1.5 times 9,000. Okay, this is 13,500. Maybe I made something wrong before. Plus the mass of the water times, this is 4,180 times 40, okay? 4,180 times 40 is 167,200, and this should be 0, right? Now the mass of the water is going to be given by the sum of these two guys, which we put on the other side. Mass of the water is going to be 83,600 plus 13,500. They become positive because I put them on the other side. And then I divide by this coefficient, 167,200. So let's see. This is not going to give 2 kilos. This is going to give half a kilo approximately. 83,600 plus 13,500, this is 97,000 something, divided by 167,200, and this gives approximately 0.58 kilograms. Did somebody find this? Okay, that's the final result, which also looks good. Okay, we have the impression that, yeah, you have 2 liters of water, you want to cool it down by 10 degrees, you add half a liter of water. This sounds okay. Sorry for forgetting this term. Thank you, Aniel. I just had my third coffee. You know, I need 3 coffees to wake up in the morning, and sometimes when I teach at 8, I don't really have time to. It's not an excuse, but whatever. Okay, next one. It's the same type of problem. You have 3,000 grams of water. So let's do a drawing. Okay, you have 0.3 kilograms of water at 80 degrees Celsius. In a Pyrex glass, okay, and this Pyrex glass has a mass of 50 grams, and it's also at 80 degrees. Of course, it's in thermal equilibrium with the water which is inside. And now we are adding to this water, a certain mass of water at 20 degrees, and we would like the final temperature for this system to be 60 degrees. Okay, so it's the same type of problem as the previous one. You want to do it? We do it together? What do you want? Alvaro? Okay, do it. Well, anyhow, we have time. We're going to finish the program nicely, so you guys won't be missing anything next year. Uh, I don't know it by heart. You don't have it in the table which is there? Okay, so how much? Well, if you need a value, it's in your CRM table. You know, in these pages which are like this, okay, where you have the value, different values for different substances. Let me put this a bit higher. Well, it doesn't want to stay. Okay, so you have these tables here. So look for glass. No, look for verre. Sorry. Verre. PQRST, verre. You see, you have it here, verre Pyrex. And here, this is what? This is the masse volumique. The coefficient dilatation conductivité, so it's on the next page. And on the next page, you have chaleur massique. Okay, you see that? And the chaleur massique, you have different values for the solid phase, for the liquid phase, for the gas phase. It's not the same. Okay, so in your case, the glass you wanted in the solid phase, otherwise it's going to be kind of difficult to conduct the experiment. So where was it? Vers Pyrex, it's this line, okay, and the C is 0.83 times 10 to the 3, so 830. Who found 2000 something? Who was it? Hello, hello. Where? On the last page of what? What? Which exercise? The page 16. Oh my God. This is a drama this morning because this value, 2320, it's the mass volumique. It's not the C. Okay. I, or whoever wrote this exercise, I guess it's I, took the wrong value in the table. So the mass volumique is 2320, but for Pyrex glass, the C is 830. So I'm very, extremely sorry. I'm even ashamed. I must confess, this is 830 in the last exercise, 830 joules per kilogram per Kelvin. Okay, I hope this is correct. And now acrylic glass. Let me check that one too. Yeah, it's also wrong. It's also the mass volumique. Oh my God, my God. So acrylic glass, it's 1450 joules per kilo per Kelvin. I'm so sorry about that. I'm going to be ashamed for the rest of the day now. It's going to be a mess. Okay, so sorry about that. And let me check if we have other stupid values in here. No, here we don't have values. Okay. Okay, so use the value for the glass. Okay, we said 890, no, 830 joule per degree per Kelvin. Okay, you can use this value. Well, it's good I checked, actually. Okay, shall we correct it, or you need more time? Okay. As I said, we have time, don't worry. I will correct my course while you do that. Okay, can we do it? Hmm? Okay, so let me reopen that. And let's try not to make mistakes this time. Okay, so we have, let's start with the Pyrex. Okay, I will call mass of the PG Pyrex glass times the C of the Pyrex glass. What's the final temperature? We want the final temperature of the system to be 60. Okay, so the final temperature should be 60 for everybody, and the initial temperature of the Pyrex glass is 80 degrees. Okay, and then we have the water which is inside this Pyrex glass. Okay, so we have the mass of the water times the C of the water. Final temperature should be 60, and this water is also at 80 initial temperature. What happened? Are you still there? Yeah, yeah. My word suddenly popped up, and I could see nothing. Okay, mass of the glass, mass of the water, and then we add water at 20 degrees. Okay, so let's say plus mass of the water, we will call it mass of the water 20, this one, okay, because this is going to be our unknown, times the C of the water. But now this water, it should have a final temperature of 60 like the rest, but the initial temperature of this water is 20 degrees, and this sum should be 0. Okay? So now what we must isolate is this. So we must compute these terms and then do the division, and voila. So the mass of the plexi of the Pyrex glass, the mass is 50 grams. Okay, so be very careful, write this in kilograms, 0.05. Okay, times the C of the Pyrex. What did we say? How much was it? 830, right? Yes, 830. 830 times 60 minus 80, therefore it's minus 20. Okay? And then this mass of the water, we know it's the water which was inside the Pyrex. It's 0.3 kilos, 300 grams, times the C of the water, 4,180, times 60 minus 80 minus 20. Okay? And then we have plus this mass of the water 20, which is our unknown, times 4,180 times 40, and all this should be 0. Okay, so this is the equation we need to solve, and so we need to isolate this mass of the water at 20 degrees. So it's going to be these two terms which have changed sign, they are both negative. Okay, and now we are going to put them on the other side. Okay, and this is divided by the coefficient which was multiplying mass of the water at 20, which is 4,180 times 40. Okay, so now we'll compute this. It will give you some time to copy. 0.05 times 830 times 20. This is 830, that's quite amusing, plus 0.3 times 4,180 times 20. This is 25,080. Okay, and this is now divided by 4,180 times 40, which is 167,200. Okay, so it's going to give less than a kilo, and this is what? 25080 plus 830 divided by 167,200, and this is now 0.155 approximately kilograms. Is this what you found? Okay, so this one. Yes, did you have a question? There was a question? No. Okay. Okay, so now let's continue. We did all this without any state change. Okay, I remind you that a state change is when you go from a solid to a liquid, or liquid to a solid, or a gas to a liquid to a gas. But what happens when you have a state change, which we also call a phase transition in physics? It happens that you need energy for that. Well, if you go from a liquid to a gas, you need to give energy to the system. And if you go from a gas to a liquid, you are getting back energy from the system. Okay? As you know, I mean, this is a small reminder about the states of matter. In the solid state, the molecules are bound strongly. They cannot move with respect to each other. In the liquid state, they are bound less strongly, so they still touch each other, but they can move with respect to each other. And in the gas state, the molecules are no longer bound to each other. They are no longer attached. They just float, and they undergo shocks with the other molecules, which is at the origin of pressure and so on. Okay, and so you have strong bonds in the solid state, you have weak bonds in the liquid state, and you have no bonds in the gas state. And in order to eliminate these bonds, when you want to go from a solid to a liquid, if you want to break the bonds between the molecules in the solid, you need to give energy to the system. You need to increase the thermal agitation, okay, because these molecules here, they are vibrating around their stable positions. They are vibrating because of temperature. Only at 0 degrees Kelvin they don't vibrate. At any other temperature, including at 0 Celsius, which is for them already pretty warm, they are vibrating. And if you increase this vibration by heating up a solid, at some point the vibration will be so strong that it will be able to break these bonds, okay? But you need to give energy to the system in order to warm it up and pass from the solid state to the liquid state. And you need to give energy to the liquid state if you want to break the weak bonds and obtain a gas. This is the fourth state of matter, which is plasma. We will not be concerned here. Plasma is a state at very high temperature. We are not going to discuss that, okay? And so there is a state change from solid to liquid, and this happens at some precise temperature. So if it's water, it's easy. You know that for water, it's at 0 degrees. But if it's for another substance, it's not going to be 0 degrees. Okay, so you have to look up the table to see what is the fusion temperature. This happens at the fusion temperature. Okay, and now if you want to go from liquid to gas, this happens at the vaporization temperature. Okay, and if you go from a gas to a liquid, now it's different. You are going to receive energy from the system, and this will happen at the liquefaction temperature. And then if you go to a liquid to a solid, this is going to be at the solidification temperature. But by the way, the fusion temperature, the solidification temperature, they are the same. This is 0 degrees for the water. And here they are also the same which is 100 degrees for the water, but it's not 100 degrees for the other substances. Okay, if you look at the melting points, there is a table here. Okay, be very careful. Water, you see in this table, water is the only substance that melts at 0 degrees and that boils at 100 degrees. And this is because of how the Celsius scale was defined. Okay, Celsius defined his scale based on the states of the water. But now if you look at all the other substances, they are not going to have the same temperature, so be very careful. When you have a fusion, look for the fusion temperature. Okay, you see that lead, for instance, has a fusion at 327 degrees, aluminium 660, etc., etc. So we will need to take this into account. Okay, and then how much energy is necessary to change the state of some substance? Okay, so let's do a little drawing. It's not in the course, so it's nice if you do it now, this drawing. Let me put that back in the right position. Okay, you all did, I guess, at the cycle, this experiment where you boil water and you look at the temperature and how it evolves. Okay, I guess you all did that. Okay, when you warm up water, let's say let's say you have water at 50 degrees Celsius. Okay, and this is a time axis. Okay, let's suppose you are warming up, you are giving energy to some quantity of water. For some time, the temperature of the water is going to increase. Is it going to increase like this forever? No. What happens? Okay, so when you arrive at 100 degrees, this is of course ideal. This is at sea level. If you boil water in Geneva, it's not going to get to 100, it's going to get to 98, because Geneva is a bit higher than sea level. Therefore, water boils at a temperature which is a bit lower than 100 degrees, like 98. Okay, but let's consider it boils at 100 degrees. Then here you will have a plateau. You will have a time during which you give energy, you continue warming up, you continue heating up, but you give energy to the water, but this energy is not used to increase the temperature, it's used to break the bonds. Okay, and when all the bonds between the molecules in the solid are broken, then the temperature can continue going up. Okay, and what do you have if I draw the states of matter? Okay, here what do we have? At the beginning of this plateau, we have water. Okay, it's been water which we warmed up, so here we have water. What do we have at the end of the plateau inside the same container? Why do you want to have a mix at that point? I did it at the end of the plateau. Okay? Okay. In the middle of the plateau, you will have a mix. So you will have, let's say, a part of water, which is still water, and the rest, which has been transformed into steam. But at the end of the plateau, okay, you have only steam. The phase transition, the state change has been done, and here you have only gas, and therefore you don't have any more bounds to break, and the temperature can go up. So what does it mean the temperature goes up in a gas? It means that the molecules, they are more agitated. Okay, they undergo more shocks between them, they move more fast, etc. And if I do the same drawing for a liquefaction, for fusion, okay, let's admit that this is not at 100 degrees, but at 0 degrees, and we start at minus 50 degrees, then what do I have here if I'm at 0 degrees at the beginning of the phase transition? Here I have what? I have ice, okay? So I will draw this in this way to illustrate this is a block of ice. When I get to 0 degrees with some ice which was at a lower temperature, here I have ice at 0 degrees. What do I have at the end of this plateau? What do I have? If I have ice at the beginning, at the end I will have water. Okay, so here I have water, and in the middle of the plateau I have some ice which is left and some water because it has already partly melted. Okay, so along this area, the quantity of water which has been transformed into gas, or the quantity of ice which has been transformed into water, is proportional to the time you spent heating up along the plateau. Okay, so let's say if it takes you, let's assume, I will say n'importe quoi, let's assume it will take you 100,000 joules to go over the whole plateau. If you have only 50,000 joules, well, you will transform only half the ice into water. Okay, you will stop in the middle of the plateau. This is all proportional, providing you are heating up with the same power during all the procedure. Okay. Okay. Now, what do we use when we compute things? We use the so-called latent heat. The latent heat is a quantity which tells you how much energy you need to go over this plateau. Okay, so we have a latent heat for fusion. Okay, and this latent heat for fusion, let's take for the water, let's look for it together. Let's take the CRM table, which was here a minute ago. Okay, let's take the CRM table. Let me put this higher up. We go into these same tables as before, these ones. We look for water. Yeah, it's O. I was looking for W. Okay, O is here. Okay, and you have, am I on the first page? No, I'm on the second page of the table. You know, there's 2 pages every time. And so for water, the fusion temperature is 0, the boiling temperature is 100, and then here you have chaleur latente, fusion, and chaleur latente, vaporisation. Okay, you see that this latent heat, it's very high, 3.3 times 10 to the 5, and it's given in joules per kilogram. Okay, so let me write down this value. You don't see it on the camera. It's 3.3 times 10 to the 5. Okay, 3.3 times 10 to the 5, it's 330,000 joules per kilogram. Okay, this is the quantity of energy in joules that you need to transform 1 kilo of water into 1 kilo of ice into 1 kilo of water. Okay, of course, the more substance you have, the more mass you have, the more energy you will need. So this latent heat tells you the energy per kilogram. Okay, and now how much energy is needed to melt completely, let's say 2 kilos of ice. Okay, let's compute that. To melt completely 2 kilograms of ice. Okay, what's the quantity of energy? Well, the quantity of energy now will be given by the mass times the fusion latent heat of water. Okay, because this is in joules per kilo, so you multiply it by the number of kilos, and you find the energy which is needed. Okay, so the mass, if it's 2 kilos, LF it's 330,000. This is going to be 660,000 joules that you need to liquefy, to melt 2 kilos of ice. Yeah. Mm-hmm. No, 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 because the LF of salt would mean you take pure salt, okay? And so this is very different. No, if you want to use salt water, you need to have the values for salt water, which are going to be a bit different, but not dramatically different, okay? But you cannot like that do a measure. You know, these are quantities that we measure, okay? This doesn't come out from any theory. We take the different substances, we heat them up, and we see how much energy we need. And there are people who are specialized in making these computations, okay, these measurements. It's like the chaleur massique. There are people who compute that. Well, they are in a lab, they measure it, and then they compute it, and they publish the values, and we have the values, okay? But this doesn't come from a theory. Okay, so now, what does that mean? It's summarized here in the course. There was a bit of a problem when passing from Word to PDF. I mean, this says QF is equal to MLF. Sorry, I should use the same F, otherwise it may confuse you. Okay, QF is equal MLF. So this is the quantity of energy you need for the fusion of a certain mass of a substance which has a latent heat LF. And here for vaporization, QV is equal to MLV. Okay, what is, well, you know that, okay, what is fusion, what is vaporization? This you know. Okay, you have the gas, you have the liquid, you have the solid. If you go from the solid to a liquid, it's fusion. A liquid to a gas, it's vaporization. A gas to a liquid, it's condensation. A liquid to a solid, it's solidification. Okay, and now what if this is for melting some quantity? What if you want to go the other way? What if you want to solidify a certain quantity of water? Well, the quantity of latent heat for solidification is just minus the quantity of heat for fusion, and the quantity of heat for condensation is just minus the quantity of heat for vaporization. Okay, it just expresses the fact that if you go from a solid to a liquid, you will need to give energy to the system, and if you go from a liquid to the solid, you will get back the energy from the system, because the energy that is in the water, in the liquid, which is higher than the one in the solid, you're going to get it back. Okay, well, let's do some exercises, and let's start with something simple. Can you answer this exercise 1? Don't worry, it's easy. Try to do it. So maybe the LF of lead, we can look for it if you want, or you have your tables. If you have your tables, you can look for it by yourselves or on Google. Just going to look for it. Can I do it? You done? Hello? No. Bon. Okay. Have you disappeared? Yes, you have disappeared. You're still here. Okay. Well, let's do it. So now the quantity of heat you need, okay, it's for lead. You have a certain mass of lead, and this lead is at 20 degrees. Aha. So let's be very careful. And let's do a small drawing. I advise you for this kind of problems to do a small drawing. To draw the diagram of temperature versus time during the phase transition. Okay, you have lead at an initial temperature of 20 degrees. Okay, and this is lead. So the lead is going to transform into, the solid lead is going to transform into liquid lead at what temperature? You need to know that. Okay, you need to know the fusion temperature of the lead. Okay, because it's not water, it's lead. It doesn't melt at 0 degrees, but if you look in your table, okay, maybe you see it here, lead has a fusion temperature of 327.5 degrees, which is not very high. Lead melts easily, okay? And this is the quantity of heat which is needed to melt 1 kilo of lead. Okay, so we are going to take these numbers. 327.5 as a fusion temperature. It means that the temperature has to go up to 327.5, and it goes up pretty linearly if you heat it up before we heat the plateau. Okay, and then we have this plateau, and once the plateau is finished, we continue, and here we have liquid lead. Okay, and this we can still heat it up until the vaporization temperature of the lead, which is 1740 degrees, but this we don't need. What we need is just this. Okay, you're following me now? And so we said theta F is 327.5 degrees. Okay? And when you have this kind of problems to solve, what I suggest you is to give names, numbers to these different phases. And these different phases, they will need to be treated separately because it's not the same. Okay? Heating up solid lead to make it reach the fusion temperature does not require the same term in the equation as liquid melting the lead. Okay, so now, well, let me erase that. So now we are going to compute the total quantity of heat which is necessary to melt the lead. Okay, is this an equilibrium problem? Huh? Well, no, this is not an equilibrium problem. This is just a problem in which we compute the quantity of heat. And to make it clear, I will separate this into two terms. One term that corresponds to this phase, one term that corresponds to this phase. Okay, and now we are going to write down these two terms. The first term, you know it. Okay, what's the form of this term? How would you write it? This is the mass of the lead times the C of the lead times the final temperature, which is 327.5, minus the initial temperature, which is 20. Okay, and this gives you a certain quantity of energy that you need, because you need to bring your lead to the fusion temperature. Okay, so let's compute it. What was the mass of lead? It was 50 grams. Okay, 50 grams is 0.05 in kilos. Then the C of lead, it's 130, if my memory is right. Is it okay? 130? Let me check, but I'm pretty sure we have it in that table. Sorry? 130. So lead has a ridiculous specific heat of 130, and this is now times 327 minus 20, so this is times 307.5. Okay, so let me compute that. You will see that it's not going to be very big, this quantity of energy, because the lead has such a low C. It's 0.05 times 130 times 307.5, and this gives us 1998.75 joules just to warm up the lead. Okay? So that was for the first phase. Now for the second phase, we have a fusion. It's no longer a phase of heating up the material. During the fusion, the temperature doesn't change. We are just breaking the bonds. And to break these bonds, we need an energy, which is the mass of the lead times the latent heat of the lead. So here we have mass of the lead times the latent heat of fusion of the lead. Okay, I'm going to write it like this to make it clear. So this is, let me write lead in all letters. This is mass of the lead times the fusion latent heat of the lead. Okay, the mass of the lead is 0.05, and the latent heat of the lead, you have it here. Okay, chaleur latente, fusion, choose the right column, not vaporization, fusion, and you have the value here, 0.25 times 10 to the 5. Okay, so it's 0.25 times 10 to the 5, and so it's 25 times 10 to the 3, so it's 25,000. You see that it's much lower than the value for the water. Okay, and now I can compute that. 0.05 times 25,000, and this gives us 1,250 joules. Okay, so you see it's not negligible at all. This is usually it takes a lot of energy, this phase, not for the lead, but for the water, for instance, it takes a lot of energy. And now the total energy we need for this transformation, for going from here to here, is of course going to be the sum Q1 plus Q2, so it's 1998.75 plus 1250, and so this is how much? 1998.75 plus 1250, that's 3,248.75 joules. Okay, this is your final result. This is how much energy you need to warm up and melt 50 grams of lead. Okay? You're welcome. Okay, so now what? Well, we need to leave some stuff for the other courses. You want to do one more exercise, or I give you an exercise as a homework and we continue next week? What do you prefer? Let's do one more. You want to do one more, or you want to take it as homework? I prefer if you do it at home, because if you do something at home, usually you do it the night before. So when you come to the class, you know what you're talking about. Whereas if you do nothing during the week, you come to the class and you have forgotten everything. Okay? Try to do it. This is an interesting exercise because you see we have 1 kilo of water at 10 degrees and 1 kilo of ice at minus 10 degrees. Okay? And what is the equilibrium temperature? Well, you should find a way to determine that, and how much water and how much ice will be at equilibrium. It's not completely obvious, this exercise. You have to think a bit. Okay? In other words, if you draw your diagram, okay, of the temperature as a function of time. You see here, temperature is a capital T, time is a small t. That's why I've been insisting so much all the time that you use small t for time, because we are physicists, and for us, small t is time. We are not chemists. Chemists, when you say T to a chemist, he immediately understands temperature. We don't. Okay? So, we have 1 kilo of water at 10 degrees and 1 kilo of ice at minus 10 degrees. So what's going to happen, you think? We have 1 kilo of ice at minus 10 degrees, and this is 0 degrees, and we have 1 kilo of water, 1 kilo of water at plus 10 degrees. What is going to happen? The ice is going to melt, okay, which means first of all the temperature of the ice is going to increase up to 0, okay, and the water is going to cool down also, and then we will be somewhere on that plateau. So this water here, it will follow the diagram by coming down here. The ice, it will follow this diagram by coming up, and there will be some point of equilibrium between the two substances. Okay? So the way I do it is usually I compute what energy it takes to do that. And this energy, I deduce it from the energy which is given by the water to do that. Okay? And then I am left with a certain quantity of energy, and I compute now over the plateau where it allows me to go. Okay, it's a bit done with hands, but that's the only way to do it. Okay, you want to try to do it? It's a fun exercise. Well, it depends on your definition of fun. You know, that's the usual thing. Fun is different. For me, it's fun. Maybe for you, plus you have the obligation to do it, so it's not as if you were free to learn that or not. Don't worry, try to do it. Okay? Okay, so I will stop here. So this is done, and this is homework for the 18 of 5. And then, since we are done with this, I still have a chapter which I didn't give you, but which we can do, which is perfect gases, dilations, and all that. I will send you the course. I will put it on Classroom so that next week you have the rest of the course, because I have a bit more than that in my course. Okay? Okay, so thank you for being online. Have a nice day, and see you sometime in the future. Okay? Okay. Bye bye. Bye bye. Bye.